Okay, so hello everyone. Today it's our pleasure to host Doug Glenzinski, the speaker of today's seminar. So many people know Doug very well since CDF times. Doug has completed his undergraduate studies in Northwestern University, and then he did his PhD in Johns Hopkins University, obtaining his PhD in 1995. Doug has been one of the very active CDF collaborators, including serving as physics coordinator at CDF. And since then take a major role in the Bpp Experiment, first serving as deputy spokesperson, and is now the spokesperson of the experiment. So Doug also served as chair of the Wilson Fellowship Committee and the vice chair of the APS Panofsky Prize Committee. So he worked closely also with TAMU, serving as mentor for our professor Roselli. And please welcome.
Do a Leatherman fellow.
Yeah, please welcome Doug.
Thank you. So we're going to talk to you today about the Bpp experiment. So what is this experiment? We're looking to search for charged lepton flavor violation via this interaction right here. So we're looking for the neutrinoless conversion of a muon directly into an electron in the field of a nucleus. It's an ambitious thing we're trying to accomplish. We're trying to improve the current state of the art by a factor of 10,000. And I like to point out that we can do that using the current Fermilab accelerator complex. Sometimes people get confused and think we need a big upgrade to the proton source. So we don't. We can do it today with the protons we have today and the complex we have today. This significant increase in sensitivity gives the experiment a discovery sensitivity to a broad swath of new physics models, and I'll talk about that a little bit more. So why is it interesting to look for charged lepton flavor violation? I think at this point it's pretty clear. We know quarks mix, we've known that for a long time. We've recently come to understand that neutrinos mix. So at this point it'd be pretty surprising if the charged leptons didn't mix. So in fact, most new physics models, there's charged lepton flavor violation. And so the question is, at what level does that occur? So strictly speaking, in the standard model with massless neutrinos, it's completely forbidden. But once you introduce neutrinos with mass and they can mix, then diagrams like this one are allowed. So it's a muon converting into an electron in the field of the nucleus. Now, in the minimal extension of the standard model that introduces neutrino mass, it's extremely suppressed. So it occurs at a rate of about 10 to the minus 52. We'll never have experimental sensitivity at 10 to the minus 52. So it's essentially invisible in the context of the standard model. However, if you read the literature, you find that many beyond the standard model hypotheses predict enhancements of the rate by 30 or 40 orders of magnitude. So it becomes something that we can observe with next generation charged lepton flavor violating experiments and MUDE in particular. So MUDE isn't alone in pursuing discovery science via charged lepton flavor violation. There's a very active global program looking for these sorts of interactions, these sorts of processes. This table shows you the current limits and then what next generation experiments hope to achieve. Now, in this whole endeavor here, the experiments which have the best sensitivity use muons, and that's just because they're very easy to make lots of them. So for example, MUDE will make as many muons in 1 second as the flavor factories will make taus in a year. So that lets us probe very small branching ratios, very small conversion rates. And they also yield very clean experimental signatures. And so in the muons, there are 3 main decays that people look for. So there's a muon decaying to an electron and a photon, so MUDE gamma. And so the MEG collaboration, MUDE gamma, they takes data at PSI in Switzerland. A couple of years ago, they published the limit that's shown there, about 6 times 10 to the minus 13 for that branching ratio. They are currently being upgraded, and they'll begin taking data, I think, later this year, early next year. By 2020, they hope to improve that by another order of magnitude. There's another endeavor, also at PSI, that's looking for muons going to 3 electrons. They have a staged approach. It's less mature, but at some point they also hope to get a factor of 10,000 improvement. And then on muon conversion, there's Mu-E, which I'm going to tell you about. There's a very similar experiment, very similar concept, and a similar time scale. That's a comet experiment, which takes data at J-Park in Japan. And of the three muons, the most sensitive channel is muon to electron conversion, and sometimes people talk about it as the golden channel because it has the best sensitivity. So in this global arena, the most sensitive search will come from Mu-E.
Can I ask you about how Mu-E relates to Mu-E gamma? In this diagram you drew, there's a photon internally in your diagram. Are those?
Yes, I'll get to that.
Okay.
So I have a slide, a couple of slides. So this global assault on charged lepton flavor violation, I mean, it makes sense not only as, kind of this optimal discovery strategy, but also it turns out that the ratio of rates, if you measure it in a couple of modes and you take that ratio, is very model dependent. So what that means is if you take these ratios, you'll be able to pick out certain models and decide that these look like nature, and you can discard the rest. And I'm just going to draw your attention to the bottom row of this paper. So these are the authors. It was published a few years ago, but everything in here is still valid. And that bottom row shows the ratio of muon to electron conversion relative to Mu-E gamma. And so there's three different columns here. So this is the prediction for that ratio in a model of oneless Higgs with T-parity. And then the other two columns are minimal SUSY model, but in a region of phase space where the charged lepton flavor violation is mediated by a photonic penguin, and in another where instead it's a Higgs penguin. And what you notice is it varies by quite a bit, and so if you measure that ratio, you can pick out relative, which of these columns the data matches to, and if you measure it precisely enough, you'll even pick out particular regions of phase space within those models. So I had said earlier that Mu-E is sensitive to a wide array of new physics models. This is just one page that shows diagrams of models for which Mu-E will have discovery sensitivity. And I purposefully arranged the diagrams so that all those for which the charged lepton flavor violation proceeds via loops, I put that in the top row, and any model where it can proceed at tree level, I put that in the bottom row. And I want to do this to draw a distinction with Mu-E gamma. So if you look at this top row, if this is a photon, then Mu-E gamma also has sensitivity, right? If you just remove the quark line, you get mu to E gamma. But if that's any other neutral exchange, if it's a Higgs, if it's a Z prime, if it's anything else, mu to E gamma loses sensitivity. If the new physics that mediates charged lepton flavor violation looks like anything in the bottom row, mu to E gamma loses sensitivity. Whereas mu to E has discovery sensitivity across the board. So this is a study that Andre de Gouveia did in the context of an effective Lagrangian. So he started with the standard model Lagrangian, introduced two additional dimension 6 operators, each of which give rise to charged lepton flavor violation. And he did this to compare the sensitivity of MEG, which is shown in red, to mu to E, which is shown in blue. And so on the vertical axis is the effective new physics mass scale to which a particular experiment will have sensitivity. And along the bottom is this dimensionless parameter kappa. So all kappa did, I told you he introduced two new terms to the Lagrangian. One was a dipole operator, so it mimics any of the new physics that looks like that top row. So it's charged lepton flavor violation via loops. And the other was a contact term, so it emulates any new physics model that looked like that bottom row. And so by dialing kappa bigger or smaller, he just dialed in the relative strengths of those two terms and very generically just probed the whole available parameter space. And so if you look at the MEG sensitivity, so this is where they are now, the dotted line is where they'll be with another order of magnitude improvement. You see that they're probing new physics mass scales up to about 1,000 TeV, only if the new physics looks like that top row, and again, only if that's a photon. But as I advertised, they lose sensitivity otherwise. Whereas mu to E has excellent sensitivity across the board, and will probe mass scales up to almost 10,000 TeV. So mu to E, as I said earlier, will have world-class sensitivity independent of the new physics scenario. It has very broad sensitivity. That's in the context of effective Lagrangian. You might wonder, well, what about real models? So there's a lot of literature on this, actually. And I just pick out one table that's from these authors in this paper. They look at a whole bunch of different models. And they also look at a bunch of different flavor variables. I don't know if you can read that, but it includes, this is D-mix, charm mixing, CP violation in the can sectors, CP asymmetries, rare muon and can decays, and a few of the different uncharged leptons flavor violating decays. That's mu to E right there. 3 stars means that experiment will have discovery sensitivity to these models. So again, discovery, very broad and deep discovery sensitivity. So I find the physics case of this experiment to be extremely compelling. And it turns out the way that it probes the new physics is complementary to the way that it's probed in other experiments. So we need this experiment to take a big picture of the new physics with energy, and we all hope to uncover them in the next 5 to 10 years. This is just one slide to say the experiment is consistently ranked as very high priority in US HEP, and we've enjoyed strong support from the funding agencies. So how does it work? Pretty simple in concept. So we start with a beam of low momentum muons. The reason we want low momentum muons is eventually we just stop them so that they can interact with the nucleus to undergo the conversion. So low momentum, so it's easy to stop. Your choice of stopping target is important. We plan to use aluminum, and I'll tell you a little bit, a couple of bullets down, why we're going to use aluminum. To reach this factor of 10,000 improvement, we need to stop about 10 to the 18th muons total. Once the muons are stopped, they get trapped in orbit, an atomic orbit, around the aluminum nucleus. The reason aluminum is nice is it has muon has a fairly long lifetime, about 864 nanoseconds. And that turns out to be important for discriminating what would otherwise be a limiting background. And let me just explain that for a moment. One of the things that lets mu to E plausibly contemplate a factor of 10,000 improvement is that we're going to use a pulsed proton beam. So previous versions used DC beam, effectively DC beam. And the reason that's a problem is, how do you get muons? You first make pions and you let them decay. So there's always some pion contamination in your muon beam. And pions, once they stop in the target, immediately get captured by the nucleus. And they can radiatively, they can get spit off a photon in that capture process, which can convert and then give you an electron that looks like signal. But it's a prompt process. It happens immediately. And so what we do is we have pulses. So our proton pulses are about 1,700 nanoseconds apart. So about 2 muon lifetimes in aluminum. And what we're going to do is we're just going to blind ourselves to the first few hundred nanoseconds and let all the prompt backgrounds do whatever they want. Whatever pions happen to have survived, we suppress them by another 9 or 10 orders of magnitude by waiting that few hundred nanoseconds. And because the lifetime in aluminum is long, we still have a large fraction of our signal left. So we're going to blind ourselves for a few hundred seconds and then open our eyes and look for active electrons. So that's the last thing. We look for events consistent with our conversion process. And what does that look like? It's pretty simple. It's a coherent process. So it's an aluminum 27 nucleus in the initial state. It's an aluminum 27 nucleus in the final state. And the experimental signature is an electron and nothing else, and it's monoenergetic. And we know what the energy is. So nuclear physicists can calculate this to good precision. And so in aluminum, it's the mass of the muon less the recoil energy and less the binding energy. And it's a shade under 105 MeV. That's the second important handle we have for discriminating background. In this experiment, 105 MeV is high energy. Okay? Which the only thing that's relativistic at 105 MeV is the electron itself, and that becomes important later on. So we have timing, and we have this monoenergetic signal. The single event sensitivity that we're aiming for is about 2.5 times 10 to the minus 17. And to get this discovery sensitivity that I advertised, that covers this broad range of physics models, we need to suppress our backgrounds by a large factor. So let's talk about that. We have 3 classes of background. The first I label intrinsic. So they scale with the number of stop muons, just like your signal. You're never going to get away with these. If you want to push to more sensitivity, you're going to have more stop muons, you're going to have more of this background. The second class scales with the number of late arriving protons, and I'll go over that. But it's that prompt process that I talked about before. So that delay only works if your pions don't somehow arrive late. And then there's also decay and flight backgrounds. And then there's the miscellaneous stuff. The most important are antiproton induced and cosmic ray induced. So I'll go over each of these. Before I do that, let me show you our expected yield. So to reach our final sensitivity, it's 3 years of physics running. And at the end of that, this is what we think our background expectations are. It's much less than that. So our dominant background comes from decay in orbit. So when you stop muons and they're captured in orbit, they do one of two things. They either decay or they're swallowed, they're captured on the nucleus. And the fraction of those two processes depends on the target nucleus. So in aluminum, about 40% of the time the muons decay while in orbit. And it's a standard muon decay, just like they do in vacuum. And this here shows you the energy spectrum. So you get something that looks pretty much like the Michel spectrum, except there's this tail. And the tail happens because of the recoil off the nucleus itself. And if you blow this up, the tail goes all the way out to the kinematic limit, which is 104.96 MK, which is right where your signal is. Now it's space limited, so it's really steeply falling. Its falling is about e to the 5th. It's really small numbers out there, but I'll remind you we're aiming for single event sensitivities on the order of 10 to the minus 10. So our handle on this background, or the amount of this background that we eventually see, is totally driven by the resolution of our spectrometer. So we have very tight requirements on that I'll talk about later. This accounts for about half of our total background. It's about 0.2 events.
Your systematics on that would probably be small because you've got statistics all the way out, though, right?
Yeah, so right now we estimate it to be about 30%, and part of that is because of theoretical uncertainties on exactly what the spectrum looks like out here. So we're working with theorists to include higher order corrections. That's what's missing right now. But that's right. Actually, the sensitivity I show you right now is all just cut and count, but clearly we will do something more sophisticated, and we have people who play with doing fits, just like you're saying, and it improves, definitely improves the uncertainty. The other intrinsic background comes from muon capture. It happens 60% of the time on aluminum. It turns out it's not important at all as a background, but I do want to mention that when the muon is captured, the aluminum becomes a magnesium nucleus. It's in an excited state. And so on average, it spits out 2 photons, a neutron, and a tenth of a proton. And that turns out to be a dominant source of occupancy in our detector. And that'll come up later. Late arriving backgrounds, this is the second category, arise from things that arrive late at the production target. So let me just go to this picture again. So in this picture, our proton pulses are these very narrow, extraordinarily clean things, right? I don't show another proton in between our 2 pulses, but that's not real life. There's always a tail, and stuff comes dribbling in. So clearly, if a proton arrives at our production target close to our delayed live gate, and it generated a pion that shows up here, this 700 nanosecond delay doesn't do us any good. And so we have a requirement that the ratio of out-of-time protons to in-time protons has to be smaller than 10 to the minus 10th. And we call that extinction. And we need to extinguish the out-of-time beam, and I'll tell you later how we do that. So that's this requirement right here. These are all the sources of out-of-time background. The only one that's important is the radiative pion capture, and that's the process that I alluded to earlier. If a pion makes it all the way to the stopping target, it interacts strongly, so it immediately gets swallowed by the nucleus. 2% of the time it radiates a photon. That photon, the energy spectrum of that goes all the way out to the mass of the pion, so well above our 105 MeV. And so If that photon asymmetrically converts in any upstream material, you can get a high energy electron. Now, if you look at that table, they only account for 10% of the total background, so it doesn't look like much of a problem, except they scale linearly with the number of out-of-time protons. So if you get that wrong by factor 2, this becomes factor 3, 4, 5. It can get away from you pretty quickly. So again, the key there is extinguishing these out-of-time protons. The last category of backgrounds I've labeled miscellaneous. There are two important ones. Our primary proton beam is an 8 GeV beam that's above the antiproton reduction threshold. So we will be making antiprotons. But they are very small kinetic energy. And they basically wander very slowly up our transport line, and they basically make a DC gas. Okay? So again, this pulsed structure is not helpful to us in this instance. And the problem with antiprotons, of course, is once they meet a proton, they liberate 2 GeV of energy, and they can produce multi-pion final states. So if an antiproton annihilates close to our stopping target, it gives a pion, the pion stops, it does this radiative capture process, and you get a background. And so we need to eliminate antiprotons upstream of our production target, or our aluminum stopping target. The other important sorts of backgrounds comes from cosmic rays. So they can decay in flight, or they can interact with material to give us a high energy electron. And so we need to employ active shielding, passive and active, to suppress that and to identify through-going cosmic rays. In the background table that I showed you, we assume we can achieve a veto efficiency of 99.99%. So if I had to summarize the keys to the experiment's success, it's these 5 bullets right here. So we need a pulsed proton beam. It has to be narrow, and there has to be very few out-of-time proton beams. I didn't really talk about this because I haven't shown you the apparatus yet, but we employ a system of solenoids to trap our pions and transport our muons. And there are very stringent requirements on that magnetic field to avoid trapping particles. We need to get this high cosmic ray veto efficiency, achieve the excellent momentum resolution, and we need to eliminate our antiprotons. So we're going to talk to you about the experiment, and as I go through, I'll try to highlight how we accomplish each of those things. So firstly, how do we get our proton beam? We begin by using protons, slamming them into a tungsten target to produce pions. We capture those and let them decay to muons. Our protons start in the booster, so that's 8 GeV. We put them in the recycler and we bunch them. And then we extract those bunches one at a time. So this triangular thing used to be used to make antiprotons for CDF and D0. It's now repurposed to provide muons and protons to a muon campus. So the G-2 experiment that we've included on the drawing here is out here, and so is mu to E. The circumference of the delivery ring is 1695 nanoseconds. So that's where we get our pulse spacing that we need. Each time the proton pulse comes around, we just peel off a little bit of it and we send it to mu to E down here. One of the advantages that we have relative to our Japanese colleagues on Comet is that we can run simultaneously with the rest of the Fermilab program. We have enough ticks in the accelerator clock cycle, and we have enough protons that everyone can get what they want, and we all can be running at the same time. That makes program planning a lot easier. This is a table that summarizes some important numbers relative to our proton beam. So we're going to get our pulses, about 25,000 at a time. Each one of those will have about 40 million protons on target, and our average rate is about 6 10 to the 12th protons per second. We have a duty factor of 25%. So if you put all the numbers together, that's an 8 kilowatt beam. And as I said earlier, they're 8 GeV protons. As I mentioned earlier, it's extremely important for us to eliminate out-of-time protons. And this is one slide that advertises how we're going to do that. We're going to do it in 2 steps. The first step we call intrinsic extinction, because you kind of get it for free in the recycler. So I told you we have to rebunch things, so we have 22.5 megahertz RF, and anything that is not in sync with the RF starts to drift, and you put collimators in the right place, and you just eliminate the first 5 orders of magnitude of out-of-time protons in that way. The second thing we're going to have is upstream of our production target is an AC dipole. Things that are in time will not be affected. Things which arrive early or late will get swept into collimators. And that provides another 6 or 7 orders of magnitude elimination of out-of-time protons. And the product of those things, remember, we needed 10 to the minus 10, and we designed a system that gives us a factor of 10 or 100 safety factor, which we're comfortable with. It's hard to model all of this exactly, right? So we want big safety factors.
Is there like a fundamental limitation with the proton flux that you can get on the previous slide? Because it presumes
Well,
if you would have 100 times more, right, the sensitivity was.
Yes. So from the accelerator side, if no one else was running, no, we could take the whole duty factor and it would go up by a factor of 4. The experiment, there's radiation safety issues, there's cooling of the production target, all of that would not be designed to handle 30 some odd kilowatts. But fundamentally from the accelerator point of view, no, we could go higher than this. But you know, what we're getting from the booster is the most that the booster can do. So if you wanted to go, so that factor of 4 just comes from, you know, exploiting the duty factor. If you want to go more than that, you need a different proton source, which we're thinking about for our next generation. Okay, so this is what the apparatus looks like. It consists of 3 solenoids. The first one is the production solenoid, the second is the transport solenoid, then the detector solenoid, and the whole thing end-to-end is about 25 meters. And the largest diameter is about 2 meters. So the production solenoid houses our production target. So in this picture, it's shown as a little red dot. In reality, it's a piece of tungsten about the size of a pencil. We put it in the middle of this high field magnet, so it's 4.5 Tesla on the far end and 2.5 Tesla on this end here. And our 8 GeV protons come in from the upper right-hand corner here. So the job of that solenoid is to collect and focus backwards going ions. And we focus them into our transport solenoid, which is this S-shaped solenoid. So this provides, it's a 13-meter path length. It's got a inner radius of 0.5 meter. And its job is to sign select and momentum select the beam. And so the way it does that is through this first curve right here, as these charged particles go through that toroidal field, they separate in the vertical plane by charge. And so this collimator here that's in the middle, at the top it's just solid, and we range out all the positive particles. And on the bottom it's shaped to only pass through low momentum fields. And then we have a second curve. So these curves, in addition to helping us charge select and momentum select the beam, it also eliminates line of sight neutrals from the production target. And this second curve eliminates line of sight neutrals from that collimator. That's the job of our transport solenoid. And then we have the detector solenoid. I should mention that the field in the transport solenoid is also graded. It starts at 2.5 Tesla here and it ends at 2 Tesla. Our detector solenoid is 11 meters long, 2 meter radius about. The upstream portion is also a graded magnetic field. It starts at 2 Tesla, and just before our tracker, it's 1 Tesla. And then it's fairly constant after that, through the tracker and the caliper. In that graded field is our aluminum stopping target. It's a set of 34 thin pieces of aluminum foil, very accurate aluminum foil. Now the graded field here helps double our geometric acceptance. So some fraction, remember the muons are stopped, so everything that's happening in the target is isotropic. And some fraction of things that start out going backwards, when you have a graded magnetic field, you trade transverse momentum for longitudinal momentum. And so some fraction that go backwards, you turn around and go in this direction. The other job of that graded magnetic field is it eliminates any background from the primary beam, because it all gets pitched forward as it goes through this graded field. As we trade any transverse momentum it has, gets turned into longitudinal momentum, and it just goes right down the middle of our tracker and the calorimeter, and we don't care about it. So it serves those two purposes. And then downstream is our tracker. Not shown on this picture is a cosmic ray beta detector, which I'll tell you about, and a few other detectors that we use to monitor the quality of the beam, including measuring so that we can demonstrate we've achieved this extinction of 10 to the minus 10, that we've eliminated the out-of-time contents. I already talked about the great field. This concept, it's very clever. This will be the most efficient and high, most intense muon source. And just to give you a feeling, right now the king of the world is PSI. They generate about 10 to the 7th muons per second, and it takes them a megawatt. We're going to generate 10 to the 10th with 8 kilowatts. This was an extremely clever idea, putting your production target in this highly graded field. It turns out to be really efficient. And it was originated actually quite a while ago, and we're excited to make it reality. We are well along. Everything is driven. The schedule for this entire project is driven by building those 3 solenoid magnets. We started a campaign of developing. We need to develop 4 different types of superconductor to make all of that, and that's well along. So these are just some pictures. This is something that says everything we're producing is much better than our specifications. We need 75 kilometers total. We have 60 kilometers now. We're going to be done with that at the end of this year. So that's good.
I have a question about are you going to talk about the detector, how you detect the electron?
Yes, yeah. I'll go through all that. This is a table of our solenoids. I think I went over this, most of this already. So in the end, we need to wind about 65 coils. And most of them are in that S-shaped thing. We need to wind 52 separate coils and stitch them together. The 2 cylindrical ones on either end, the production and detector solenoid, are being built by General Atomics in San Diego. And that S-shaped one, these 52 coils will be wound and produced in Italy, and we will cryostat them and stitch them into the S at Fermilab. So this is a prototype of 1/27th of that S that we built and we tested, and it performed fantastically. And so based on that, we told these vendors to start building. So that solenoid is being built now. And the other one, we have a final review in April. And if that goes well, we go to General Atomics thumbs up to start winding all these coils. This is one slide. I'm not going to go over it too much, only to advertise that we've spent an enormous amount of energy convincing ourselves that this magnet that we've designed is going to let us do the physics that we want to do. So these are just plots that show the specifications and then what the field is. The different colors are at different radii. So here it all has to be negative, and this is 3 different radii. This is over a particular section of that S-shaped magnet. But we didn't do it. So all of these are made assuming perfect alignment, perfect conductor. But we also took it a step further. We introduced misalignments. We introduced imperfections in our conductor and generated, and then we just reproduced the whole field map. We would jiggle everything randomly. And we did this a few hundred times and generated several hundred maps. And we found the worst case ones, the ones which were the ugliest. We repeated all of our physics sensitivity studies and found that if they build these magnets to the specifications that we demand, which are typical, okay? We're not asking them to do anything that's outrageous. We're going to get to do the physics, even in the worst case scenario. Even if we just get unlucky and everything, systematically gets messed up, we're still going to get it done. We have a lot of confidence in the design of this. So some numbers: 7 trillion protons to the production solenoid each second, 26 billion muons through the transport solenoid, half of which stop. So after 3 years of running, that's 1 quintillion stop muons, so a billion stop muons. And I was giving a public lecture. I wanted to, for what a quintillion is. So it turns out some engineers had to do a little exercise to predict how many grains of sand there are on the beaches of the Earth, and it's about a quintillion. So we're going to stop a muon for each grain of sand on the face of the Earth, and we're going to sift through all that and find the 10, 100, whatever, depends on what physics says, look like muon to electron conversion. So let's talk about our detector now. How are we going to find these electrons? So this is a little bit more detailed drawing of the detector solenoid. So here's our stopping target. So these are aluminum foils. In that previous picture I did not show, but we have a very thin piece of plastic. It's an absorber. So remember I told you we're stopping 10 to the 10th muons per second. 60% of them are captured. And for each capture we generate photons, neutrons, and protons that would just light up your tracker. And so we want to get rid of some fraction of those by putting them there. We don't get rid of all of them, but we get rid of quite a few. And then this is our tracker, and that's our calorimeter. We only stop half our muon beams, so we design a beam stop that stops the rest of it while minimizing backscatter. So I'm going to go through the tracker, the calorimeter, and then again, I haven't yet shown you what the cosmic ray detail looks like, but I'll talk about it. So our tracker, it needs to be low mass in order to achieve the spectrometer resolution that we need to achieve. Our resolution is entirely scattering dominated at 100 M. So we're looking at a, I should also say, this is in vacuum, 10 to the minus 4 torr. That's to eliminate scattering of beam particles into the detectors. That just is an additional challenge for the detectors we need to use. So we're employing a straw tube technology. So this is a picture of one of our straw tubes, 5 millimeter diameter. The thickness of the walls is half as thick as anything anyone's used before. So we're using 15 micron thick mylar. It's metallized on both sides. And 25 micron gold plated tungsten wire. Argon CO2 is our pressure gas. This is the geometry of our tracker. The fundamental unit we call a panel, and it's 1/20th of a circle. Okay, it's an arc of 100, not 1/20th, 1/3, 120 degrees. And it has 96 straws arranged in 2 layers, and they're offset from one another. So you have 48 straws on top, 48 at the bottom. And if you stitch 3 of those together, then you cover 360 degrees. And so we take 6 panels and we rotate the front and back relative to each other, and you get nice coverage in a full azimuth. And we're going to stitch somewhere between 36 and 40 of those together to make the full tracker itself. This is a picture. If you stitch 2 of these planes together, we call it a station. This is in the transverse plane. So the muon beam is into the page here, and the trackers are here. So it's a transverse tracker. It's like a forward tracker. Well, the reason we like doing this, the reason this is a great thing to do, is it moves all of your readout electrons in your gas manifolds to large radii outside of the active bond. So it keeps a very low mass in the active region. In the end, we're going to need about 20,000 straws to produce a whole tracker. We've begun building prototype panels. I guess I should say, the inner radius here is 38 centimeters, and the outer radius is 70 centimeters. And the straws range from about 30 centimeters up here to 1.3 meters at the longest one. And so that just kind of sets a scale. That's our first panel. This is some postdocs installing and testing some electronics on that outer radius, and we begin testing that. So when you stitch the whole thing together, this is assuming we have 18 stations, and we have gaps here to install other ones later. You know, it's always about money. It's over 3 meters long, and that's important because the electrons that we're looking for will, on average, complete 2 full turns of the helix. And it turns out that completely eliminates, basically, misreconstructions from accidental overlays. It's very difficult for things to accidentally line up here and then reproduce the same thing another 1.5 meters downstream. You will notice that the inner 40 centimeters of this is empty. That's on purpose. Remember, 40% of our 10 to the 10th muons per second are going to decay. And by keeping that inner 38 centimeters hollow, we blind ourselves to over 99% of this decay in orbit. Otherwise, would be a serious occupancy problem, if not a background problem. We just don't care about it. We don't see it. Similarly, for half the muon beam that we don't stop, it gets pitched forward, we don't see it, we don't care. We are fully fiducial for everything above about 85 mm. So that's all on purpose. The hit rates that the tracker has to tolerate are things that people have done before, okay? Particularly after you've waited a few hundred nanoseconds. It's things that CDF and D0 have done. It's LHC detectors handle much higher rates. This is a picture of what the tracker will look like if you integrate over a full microsecond. So in there is a signal electron, and everything else you see there is from all these capture products, right? From the photons, neutrons, which eventually capture and generate more photons, and the protons. So that looks ridiculous. We're of course not going to integrate over a microsecond. The maximum drift time of a 5 millimeter straw in RDS2 is 50 nanoseconds. So now if you start making windows that are 50 to 100 nanoseconds wide, your tracker occupancy is about 2%, and it's pretty easy to pick out your tracks at that point. The reason I want to show this is I'm going to get to some results of what we think our sensitivity is. And what I want to advertise is the simulation that we've put together is as sophisticated as you can make it, short of having data. We simulate everything, all the background overlays. We don't know when the muon is going to decay, so we don't have a T0. You have to simulate the full microsecond, and then your pattern recognition has to decide when in that microsecond did something happen. We include that. We digitize everything. So what our pattern recognition gets is ADC and TDC. They're simulated, but we could run it on data today if we had.
I have a question.
Yeah.
So just a big picture, two questions. One is your signal, you were counting on very high resolution so that you can get rid of the other background, which are the two neutrinos. And the other thing is the choice of the nucleus that captures, because you don't want the recoil to be as small as possible. Is that a correct statement?
Well, we choose aluminum primarily because it has that long lifetime, that 864 nanosecond lifetime. Because we need to wait about 700 nanoseconds from the proton pulse to kill all the pion backgrounds. And so by having that long lifetime, 50% of our muons are still alive. So if we choose something different, it'll have a shorter lifetime, and we'll just have smaller signal after 700 nanoseconds. So aluminum is something that you can buy in high purity. It's mechanically stable, right? Those are things you have to think about if you're going to build a target out of it. And then once you collect that subset of materials, aluminum sticks out for its long lifetimes.
And your choice of detectors for the high resolution 106 MeV electron, is this, how did you choose on this?
Right, so this straw tubes, we looked at a couple of things. We looked at open, so you need very low mass, right? So silicon is out. So you're looking at some sort of drift chamber. The advantage of these straw tube drifts is that you can build them so that everything, all the high mass stuff lives outside of your active volume. So an open cell drift chamber, which we investigated for quite a long time, the problem is you're in vacuum, and so your end plates actually have to be pretty robust, and this inner, you need some inner can here. Also has to be fairly thick, and it introduces mass, and it's just very difficult to achieve the momentum resolution that we need. So straws are individually very robust. They work well in vacuum. By orienting them transverse, they don't sag. You can string them with enough tension over meter that they don't sag. And so they just satisfy all the technical requirements.
What about gas?
Yeah, so the gas manifolds basically feed one side of the straws, and then the exhaust is on the other side of the straws. So is that what you're asking? Yeah. So the readout electronics are actually just here in the top, and then gas manifolds are here and here.
And are you worried about any aging effects?
Or yes. So we've done studies up to about 2 coulombs per centimeter. What we're realizing now, based on some of these prototype tests, is we're probably going to have to operate at larger gain to get the hit efficiency that we need. And so we're going to have to repeat those studies. We think we'll have to integrate up to about 7 coulombs per centimeter. And we'll see. We've seen, as far as we've pushed it so far, we've seen no problems at all. So the people leading this effort are Seat Mukherjee and Bob Wagner, so they're very familiar with what happened.
You're golden.
Yes, with AJ at the COT, on the CDF. So yes, we are worrying about that. But all the data we have right now tells us it's going to be okay.
You will have critical peak fluxes during those beam flashes.
Yeah, that's right, yeah. So the rates that I showed you, oh yeah, right, so it shows it here. Right, yeah. So on a straw, on these very early times, it's 50 some odd megahertz. So when we estimate total integrated charge, we have to include that. We're not reading out then, so.
So you're not reading out, but still.
The charge accumulates, right. So we want to start reading out sometime after 500 nanoseconds or so. And so based on simulations and some, we've taken these things and put them in proton beams. Protons are very highly ionizing if they're slow enough, and it recovers fast enough. Yeah. Is it going to be exactly 500? We won't know until we get there, but we're designing it to start well ahead of the 700. Partly as a safety factor, partly also, if you measure early, you can measure this radiative pi capture background. It goes up by a factor of 10 for every 50 nanoseconds you go back. And so we'll be able to measure it in situ. Okay, so this simulation, which, as I advertised, we tried to throw everything in there that we can. It has all the effects that we know about. Achieves this resolution at the face of the tracker. So this is the intrinsic resolution of the tracker. I told you earlier, the core has to be better than 200 TeV. It's 100. The non-Gaussian tail here is pretty small, about 3%, and it's well within our performance requirements. This is, if you simulate a whole experiment, this blue line is what the decay in orbit spectrum will look like when this is blown up. It's starting at 100. And this is events per UDE experiment, and it's fractional events here. And then this is what the signal looks like, assuming a conversion rate of 10 to the minus 16. And this here is our signal window. And right now, we're not doing anything terribly sophisticated. We pick that window so that the DIO is 0.2. It's just what we do right now. You will be smarter. But being dumb, we almost get, we get 80% of the way where we need to be. So I'm not worried about getting the last 20% in the next 5%. We spent a lot of time understanding what our efficiencies are, where we lose things. The lion's share is just in the fiducial cut, just the way the geometry of the tracker is. Only about a third of the signal intersects that, but as I mentioned earlier, that's purposeful to eliminate what otherwise would be overwhelming backgrounds. I don't want to say anything more here. So our total acceptance is about 9%. We include, it's 9% of defined good tracks with after 700 nanoseconds, and then that momentum window. And then we employ the calorimeter for some particle ID, and we reject on the gradient. And that loses 5%.
That's it, track fit, 75%. 70%.
Yes, so that's a place where we think we're going to do better as we understand more. So in particular there, the simulation includes nonlinearities in the time to distance ratio, but our fit doesn't. It's just linear. So we know the fit, there's things the fit can be more sophisticated about, and it'll improve some of these things. We spent a lot of time worrying about systematic uncertainties, particularly as it relates to the occupancy in the tracker. So I keep saying for every neutron capture, there's 2 photons, a tenth of a proton, and a neutron. That is all experimentally measured, but not very well. And so we vary our simulation, we bump up the number of protons, the neutrons, the beam flash. This degraded thing, the tracker is not going to work perfectly, so we mimic various failures. A gas manifold fails, some readout boards fail. We take a worst case scenario. We do all these things and we look at our total acceptance. And we also look at how it affects our resolution. And the answer is our acceptance is stable to within 5% and our resolution is not significantly affected. So we're really confident that this tracker we're designing is going to deliver the performance that we need. Okay, the calorimeter. We're going to employ a crystal calorimeter because it's compact, it's radiation hard, and what we really need is moderate energy resolution, but we need good timing and decent positional resolution. The crystal of choice, we looked at several. The one we're going to use is pure cesium iodine. It's radiation hard. We're going to expect 10 kilogray total. That's not a problem at all for cesium iodine. It's fast, so it has a decay time of about 25 nanoseconds. That's good for the rates that we're looking at, and it's easy to handle.
What is hygroscopic?
It means it's not affected by water, so you don't have to worry too much about humidity or when you touch it with your moist hands. Some crystals, you damage them very easily in hand. So this is not one of them. The geometry is 2 disks, and they are also transverse to the beam line. This makes it charge symmetric compared to other things, which opens up another physics channel. It's mu minus n to e plus n, which actually is related to neutrinos double beta decay. It can only happen if neutrinos are myron. So if you observe it, you've demonstrated that when neutrino is myron. And it also, any of these radiated backgrounds, the photon can convert to positrons as well as to electrons. So by measuring high energy positrons, it's another handle on all of those backgrounds. There's 2 of them because some fraction of the time, the particles that come down spiral through the middle of this, the helix so you put this a half wavelength downstream and you catch all of those. Okay, and the radii basically match the tracker, 40 centimeters inner, 70 centimeters on the outside. And we're going to read out, we have about 2,000 crystals total, and each one is going to be read out by 2 solid state photosensors. The resolution we expect to achieve, again, including all the background and overlaying, all that sort of stuff, is about 5%, and we need better than 10%. And what drives the performance requirements on the calorimeter is actually, we use it as particle identification. You're never going to get a calorimeter whose resolution matches the spectrum. And so the thing it does is it separates muons, particularly cosmic ray muons that scatter, and they're around 100 MeV. In the tracker, you can't tell the electron from the muon very easily, but only the electron is relativistic, and so if you compare the arrival time of the particle at the calorimeter with what you predict from the tracker, you see it very easily. It's a 3 nanosecond difference between muon, 100 MeV over C muon compared to 100 MeV over C electron. Also, the E over P is very different. The kinetic energy of 100 MeV over C muon is only 40 MeV. And so E over P is also very different. And so we put those 2 things into a likelihood, and we reject, we have a rejection factor of muons of 200, and we retain 95% efficiency on our electrons. And what this just shows the performance of that as assuming a bunch of different energy resolutions and timing resolutions. So we need a timing resolution better than a nanosecond and an energy resolution better than 10%. And what we achieve in test beam is 5% energy resolution and timing resolution of a couple hundred picoseconds. So, and again, we do systematic studies of varying all the occupancies, and we meet these requirements easily. Last detector is the cosmic ray veto. This was one of the first simulation events. We saw it, scared the heck out of us. The cosmic ray interacted in that plastic proton absorber, kicked out a 100 MeV electron that just looked exactly like the same. It turns out that we get about 1 of these a day. And so we need this veto to detect this through-going cosmic ray so that we can reject those things. Turns out it can scatter all sorts of places and get into the acceptance, including that collimator that was in the middle of that S-shaped solenoid. So we have 300 meters squared of active veto detector, and the technology we're employing is extruded silicon. It's cheap, can cover a lot of area, and you get very high single layer efficiency. So we're going to build 4 layers. We're going to require coincidence in 3 out of the 4. And we need multiple layers and a coincidence because we have a lot of neutrons. And they interact, they cause accidental rates, and they can give rise to false physics. So we have achieved in a test beam the per layer efficiency that we need, over 99%. And then you can do 4, choose 3, and that gets you above 10 minus 4. We actually are much more sophisticated than that in demonstrating we can reach that veto efficiency. This is also a recent test beam, so we're going to read out our scintillator on both ends, but on a single end, a MIP gives us over 60 photoelectrons. And that's, we needed 40 something, so we're getting the idea we need. Yeah, good. I should have mentioned that. They're about 4.5 meters across. And they're 5 centimeters wide, 2 centimeters thick. There's 2 wavelength shifting fibers, and we read out each wavelength shifting fiber with a silicon photomultiplier.
So they're sufficiently small in this direction so that to reduce the number of accidental.
Yeah, that's right. It's actually, I mentioned that, I think, here. It took us honestly, about 2 years to find a shielding that we can afford and that mitigated all these neutrons and the capture photons to a level that the cosmic ray veto could tolerate. And that also involved optimizing the number of layers and the geometry. It's all tied together. Because the 2 requirements here work in opposite direction. To get really high veto efficiency, you want low thresholds. But low thresholds increase your accidental rates, and these 2 things are working in opposite direction.
How big is the square?
It's 300 meters squared of active cylinder. Might be too late now. One word about our building, that's what it's going to look like when it's done. We're over half finished. I should have added another. The below grade stuff, which is here, is all done. There's a roof on it. The walls for the upper level are just about. The concrete walls are finished, and they're going to start all the structural steel. So we'll get beneficial occupancy this summer. We spent a lot of time worrying about details. How is this all going to fit together? So there's very detailed 3D models, and there's weekly meetings to understand how we're going to install and maintain. This is a picture of a forklift. Can we get around? Can we move around? Can we actually make this thing work? This is our schedule. We'll begin commissioning later 2020, early 2021. The entire schedule is technically limited, but it's all driven by the solenoids. It just takes a long time to make superconducting solenoids, especially some of which we haven't known they're made as national before. So as I said, we're about here, and let's see, we're here. And we've started the S-shaped one, and later this year we'll start the 2 other ones, and it takes about 3.5 years to finish those. Another year and a half or so to install them, align them, commission them. We hope to take quite a bit of cosmics from the detector, so that once we get beam, we're ready to mount it. One brief slide to say we're thinking already about next generation. I think there's a very compelling case regardless of whether, if we see nothing, we want to push further. If we see something, one very nice thing about UDE is you change the stopping target material. And what you measure in that new stopping target material depends on the underlying physics. And that's what's illustrated in this table. So this is the ratio of the conversion rate as a function of a new stopping target material relative to what you measured in aluminum. So this is if it was scalar mediated, dipole mediated. One of these is a left-right symmetric model, another's a gut model. I don't remember which is which, but the point is those lines separate. So you make a measurement of 20% or something, and you're going to start picking out these lines. What's going to tell you about the underlying physics. So Mu-to-E is a very ambitious experiment. Factor of 10,000 improvement. We're being ambitious because we think we can, and because it gives us discovery sensitivity. Very broad and deep discovery sensitivity. I briefly mentioned that the way we probe this underlying physics is complementary. We do it in a way that other experiments can't do easily or can't do at all. And we're going to begin commissioning in 2020. You know, a lot of details on our technical design report or experimental website. And of course, everything here is the product of work from a very talented and dedicated population. So,
What's your data taking schedule? You showed the construction.
so we think we're going to need a 3 to 4 year finish run. I always say 4 years. We need 3 years of physics data taking, and then I add on a year for calibrations, for special background runs, that sort of stuff. It will take us, at nominal intensities, it'll take us about 90 minutes to eclipse the current Lorentz best. So we are not likely to start out at design intensity, but that's just a comment that even if we start out with a small fraction of that, with a small amount of running, we have relevant results.
So in 6 months after, you might have something really to show in 6 months after you start.
We will not turn on and run for 4 years straight. We will run for a little bit, stop, dig in, make sure we understand what we're seeing. Right, yes.
What about the targets? Are they, is there any plan to change them regularly, or are they going to just survive the experiment?
The aluminum targets just survive. The production target is a much different thing. So it's made out of tungsten, and tungsten oxidizes and kind of disintegrates, which the light bulb industry has known about for a really long time. You can find papers way back. So what we have to do is that production solenoid is operated in vacuum precisely to keep that production target alive. And right now we're aiming for a vacuum of about 10 to the minus 5 torr. And we think we will lose a few hundred microns of our production target because it warms up to about 1700 degrees Celsius at that vacuum. And we will probably swap it out each year. And so we have a whole, for radiation safety issues, you design a whole target handling system, so it's a robot which can go in, grab a spent target, drop it in a coffin. And we have a shelf of new targets, grabs it, and sticks it in. So that we're going to have to do each year. The aluminum should just be fine. We are, however, also doing R&D on a titanium target. If we're extraordinarily lucky, we could see a signal of 100 events with 6 months of running. At which point, it would be nice to have another target to swap in there to do this other measurement that I talked about. So we are thinking about it.
Wait, but with titanium, do you see the separation?
Yeah, so that's a good question. So two things, well, whenever you go to a different target, two things will change. One is the lifetime of the muon, and also the recoil and binding energy changes, so the energy of the electron changes, and the ratio of capture to decay products changes. So all of that changes. So in titanium, the lifetime goes from 864 to something like 330 nanoseconds. So, but the decay in orbit fraction falls from 40% to 15%. So it turns out that it's almost a wash. So you get less signal, but there's less of that decay in orbit background. And so it turns out to be about a wash in terms of sensitivity. But it does change.
As an outsider's question, so since you're searching for this new gamma coupling, do you think it's feasible or maybe better or worse to shoot your muon beam into a laser?
to a laser for it to interact with
Or
the-
some kind of photon beam, so, say.
Well, let's see, so how would that work? So that's mu E gamma.
Well, you
So
are
you're-
mu E something that including a photon, right? So it's pretty much the same vertex.
Yeah, well, so you would be looking for some electron coming out.
Yeah, you look for some large angle scattering of electrons.
To be honest, I haven't thought about that. So I gotta go back here. Right, so if you get rid of this line and, yeah, well, so it's through a loop.
Yeah, but your mu E conversion also has this Z. So
Oh,
it-
yeah,
it's
yeah, yeah.
beyond that. So you say your mu E gamma is one body.
Yes, yeah, right, all right. That's,
Yeah.
right, it's only for the mu E gamma vertex
Exactly.
that we're
So
talking
when you
about, but
got
it's,
that vertex.
there is no photon mu vertex here, it's all through loops. That I would have to have.
Okay, okay. So probing that W because you have charged pions.
Was it a question?
Oh, no, I was, since they're dominated by the massive bosons, I think they probably need the same order because
Yeah.
high charge pi is basically the same as a W.
Yeah.